is equal to 0, you can see this triple. You know, I already defined this symbol, which is just this. And now you can operate with the covariant derivative here. Yeah.
The definition, even though it is an Aula triangle with things below which it behaves like above.
Oh, sorry. What's happened here?
Because it's finally you.
Is that what you meant?
Yes.
Thanks. Okay, and now we can use the Klein-Moulton equation. So find modify to satisfy the Klein-Moulton equation. So this is m squared so clearly these two guys cancel out. They are both phi 2, phi 1 star and m squared plus etc. And these two guys cancel out as well. So that's a one-line proof that's a conserved current. So that allows us to define a scalar product which does not depend on the Cauchy surface. So you integrate sigma is a Cauchy surface. Integrate the current over your Cauchy surface. Again, the proof is trivial. And I used Gauss' law, which I wrote when we were doing classical field theory. So you integrate over the volume that's contained between the two Cauchy surfaces. Okay, and now we use the fact that the divergence of the current is conserved, so that to zero. And that's independent of the choice of Cauchy surface. This means two things. You can foliate the space-time. You can use different foliations for your space-time. This is telling you that it's independent of foliation. And also that given foliation, you can have a parameter t that gives you different labels, different Cauchy surfaces. So it's also independent within a specific foliation. It's independent of which Cauchy surface you choose. So it's totally independent of the Cauchy surface. So that's how you choose your inner product. Any questions? This is just a trivial generalization of what we did in flat space-time. And the canonical quantization procedure is just literally, it's formally the same. So the quantization procedure is formally in flat space-time. So we choose a complete set. The solutions of the homogeneous field equation, Klein-Morgan equation. And you, it's an orthonormal set with respect to this choice of scalar product. Just a note that what really matters is not so much positive frequency, but positive norm. That really is the crucial thing. This makes no difference in terms of bosons. It does make a difference for fermions, which we're not going to do. But this is the really crucial thing. You're splitting your solutions in terms of positive norm solutions and some negative norm solutions. Okay, this formally is the same as what we did in flat space-time. delta ij can be continuous index or discrete index, so it's a Dirac delta distribution or a Kronecker delta, depending on which case you're dealing with. And your space of solutions is just the direct sum of the positive frequency solutions, vector space spanned by the positive norm or the positive frequency solutions, and that's the same for the negative norm, negative frequency. Then you expand your field in terms of this complete set, so a general solution. So that's just formally the same as in plan space then. So far we haven't quantized anything, and now you quantize it by promoting the coefficients to operators and imposing the computation relations. So these are the equal time commutation relations. And that's equivalent to the commutation relations for the Fourier coefficients. And that's true because of this because they obey those orthonormality properties. The momentum, obviously, pi, is defined like we already did in this way. And the vacuum state, or if you wish, a vacuum state, because depending on which complete set you choose, you'll have a different vacuum state. Is the state which is annihilated by the corresponding Fourier coefficients. From that you construct a one-particle Hilbert space by operating upon it with the creation operators, and from there you build the Fock space. which is your full Hilbert space. So formally just the same as what we did in flat spacetime.
It's missing plus there, right?
Sorry?
It's missing plus there, right? And the third commutation relation after main.
Oh, it's missing a dead pattern.
Yes.
Plus, you said?
Yeah, like but at the other.
I've written this wrong. Sorry. Sorry, you're right, yes. In here. Yeah, thank you. Any questions? So I have a question. Say that you impose these equal time commutation relations, equal time because the times are the same in both phi and pi. There are different spatial coordinates of same times. If that's satisfied, if this equality is satisfied at a certain time, is it satisfied at all times? That's not a trivial question. And similarly, if it's satisfied for a specific choice of time coordinate, is it satisfied for all choices of time coordinates or foliation of your space?
The second question, I would say that it isn't.
Okay.
By changing affiliation.
Why not?
Because by changing affiliation, you might be going to a different vacuum state, so the annihilation of radial operators will be different. So there is a double arrow there, so the vacuum.
Okay, but this is different. Did you just the combination being zero or not? That's a little different from that. So the way it's written, it's not obvious. There is a specific choice of time t, but because of what they said, that the conserved current, so the conservation of the current leads to the fact that the inner product, or the scalar product, is independent of the choice of Cauchy circles, which means both things. It's independent of the foliation of your spacetime, and it's independent of the choice of slice within a certain foliation. A consequence of that is also that this is independent of those things. It is not obvious from the way it's written, but you can rewrite it in a different way. So you can consider this finish, the quantization, just a node if you wish. That these equal time commutation relations can be written in manifestly covariant form. This is the Pauli-Jordan function, which is the advanced green function minus the retarded green function. This is manifestly So if you have a general relativity mind, this is a lot more fulfilling and pleasing than this horrible little thing. You can try to do this as an exercise. It's not trivial at all, but now this is indeed very, very pleasing. One of the reasons is that it tells you causality is inbuilt, is manifestly there as well. So you have your point x. If you choose x prime anywhere outside the light cone, so G red is 0 for all x prime not in the causal path of x. Okay, the causal path is this. The advanced one is 0 for all x prime not in the causal future of x. So x advanced is 0 outside here, retarded is 0 outside here. The commutator is therefore 0 if x prime is neither in the causal future nor the causal past of x. So if they're acausally related, if there's no time-like or null path joining the two of them, the commutator is 0. So for x and x prime space-like, the commutator is 0. This does not mean there's no correlations. It just means it does not affect the value. It doesn't matter which one you observe first, x or x prime. You're going to get the same. There still exist correlations. Between space-like points. Since phi x prime may be non-zero, even for space-like points. Space-like separated points. This also shows that 4 is independent of the choice of foliation. And that if 4 is satisfied at some time t, then it also is at all times. You only need to impose the commutation relations at one time, and they're going to be satisfied at all times. Any questions?
Can these correlations affect any kind of measurement that is on a further station?
Yeah, what do you mean?
And I'm fine with the commutator being 0, so there is independence, not independence. The commutator is 0 for space-like separations, but there are two-point function correlations. I'm fine with that, given that it's not possible to use these correlations to send signals somewhere else.
Right.
So that poses it isn't possible.
Yeah, no, so these correlations just come from, say that you've got 2 points very close somewhere in the path, causally connected in the path, and then one observer, or you look at one point causally connected to this one and another point to the future causally connected to the other one. You can even look just at the same point here. Same point and then looking at some point in the future going towards the right, some point in the future going towards the left. So these two, there's going to be correlations between these 2 points because they were set up here, but they are spatial. That's as simple as that. Okay, so next week we're going to start talking radiation. How about doing the midterm exam next week? Next Wednesday. Wednesday next week. If it's too soon, we can postpone it another week.
I'm screwed in any case.
Why are you screwed in many days?
Next Wednesday is the day after my defense. Next Wednesday is also the.
So which Wednesday are you talking about?
There is next.
Next Wednesday, you mean Wednesday? The Wednesday this week or Wednesday next week?
Oh, the Wednesday this week I will not be here. I'm in São Paulo.
Okay, Wednesday next week.
It's the day after my defense.
Okay.
It's fine. Not safe. And the next week is the same. Your lecture is at the same day as Fernando's exam. So I will have quantum information exam in the morning and an exam in the afternoon.
Okay, but I mean we have to do the midterm exam in some week.
No, I'm fine. Whatever you choose, I join.
I mean next week it can be in another day, but it can be Monday, but
well, next week is fine.
okay, so Wednesday next week. Exam. So that's midterm exam. So that's a 2-hour exam. About the stuff that we have done up until this Wednesday in today's. It's not about memorizing. So you're not allowed to bring notes, but I'm not going to ask you to memorize things. I'm going to nothing complicated. You need to know to memorize the basic things, but not anything complicated. Anything that's complicated, if you need it, I'm going to write it in the exam. Complicated to memorize, that's what I mean. You need to understand things and how to do things. What about more lecturing time next week? So could next Wednesday be 3 hours and then we do an extra hour for lecturing?
I lecture right after the exam.
Yeah.
I will be there inside, but you can do it.
You will be what?
I will be there inside. My body will be here.
Okay, so another day, Tuesday then. Or Monday.
Won't be here next week, so
You won't be here.
no.
What about oh, you're not registered, is it?
Yeah, I'm not subscribed.
Let's just do next week's exam. Let's just do the exam next week. And let's do an extra lecture the following week. So what about Monday in exactly 14 in 2 weeks? Can we do a lecture then? Yeah. So Monday in 2 weeks. 2 to 4 p.m. extra lecture. Yeah. Okay, so next the exam. For the exam, I suggest throughout the course, I said on many occasions, okay, you can do this as an exercise, you can do this as an exercise, you can do this as an exercise. I suggest that you try to do those things. Some are terribly complicated. This is complicated, so not it's way too complicated for you to do an exam because you haven't done it in the classroom no more. But a lot of other ones were, simple or were simple generalizations of things that we did in the lectures. Things you should be able to do. Okay. I'll see you on Wednesday.